Good morning, everybody. In this lecture, I am going to discuss about the gas liquefaction methods. I hope you are able to see the screen well. The contents of my lecture is going to be like this. We will introduce the gas liquefaction. What is the minimum work requirement to liquefy a gas? And also we will find out what is the ideal work for liquefaction of air, various components of air. Then there are basically three methods which one normally comes across, namely the induced evaporation, isenthalpic expansion, and adiabatic expansion. So we will discuss about these three methods. Then we'll talk about the liquefaction systems for gases other than hydrogen and helium. We will also discuss about the pre-cooled Linde-Hampson system, the Claude system, the Kapitsa system, and the Halen system. So these are the different type of liquefaction systems useful for liquefying gases. We'll try to compare the above systems. Then we'll talk about the liquefaction for hydrogen and helium. Next, we'll talk about the ortho-para conversion of hydrogen, Collins liquefaction system for helium. And if you want to liquefy helium in small batches, then we will use Simon's liquefaction system. Phillips Stirling cycle refrigeration system can also be used for liquefying, let us say, nitrogen or helium. So we will discuss about this. It's a COP and on the regenerative effectiveness we'll discuss. And the Stirling cycle based liquid helium plant, we'll probably just mention about that. And probably if time permits, we'll talk about the sample problem in the area. Okay, so this is going to be the plan of my presentation today. Okay, first let us talk about liquefaction of gases, and we introduce this particular topic. What is liquefaction? Liquefaction represents a process of converting a gas into the liquid state. Now, what do we need? We need a refrigeration system because we have to extract heat from the gas so that the temperature decreases and then finally it becomes a liquid. So essentially, we need a refrigeration system wherein the working fluid should undergo a refrigerated type of cycle. Heat should be absorbed at low temperature source, and with the addition of the external work, heat is delivered at the high temperature sink. Normally in a liquefaction system, the liquid collects in the reservoir where it is getting liquefied, and part of the liquid will be removed for use. In such a case, an equivalent amount of fluid, gas, has to be added at the ambient temperature so that the cycle continues further without any decrease for want of gas. In a normal refrigeration system, there will not be any accumulation of the fluid because the refrigeration, whatever that is produced, is directly used up for cooling some other object or substance or whatever it is. In both cases, the process fluid undergoes a cycle of operations. Okay. Now let us try to understand a little more in the cycle of operations of the refrigeration system. You start with an ambient compression of fluid, and then the heat is rejected to your coolant. Normally when you compress a fluid, the temperature rises because you will be doing an isotropic process of compression, and the heat will be added to the system. Although in principle it is supposed to be isothermal, but practically it will be isotropic, and heat will be added to the gas. It will become hot, hot compressed gas and the heat has to be rejected to a coolant. This is to essentially decrease the enthalpy and the entropy of the fluid. Now, this hot gas, originally now cooled back to ambient temperature, but at high pressure, has to be cooled by the compressed fluid, which is returning, okay, in the opposite stream in a heat exchanger. Okay. Now, the gas will become cold just before the Joule-Thomson valve. Now, gases expand at the Joule-Thomson valve, or maybe it will be cooled further in a piston cylinder arrangement, which is isentropic expansion, wherein the enthalpy and the temperature decreases. Okay, so you will be now be decreasing the temperature of the gas and also its enthalpy. Okay, and at cryo temperatures now, heat is absorbed by the fluid. It again increases its entropy and enthalpy. In the case of liquefaction, liquid is withdrawn, as I mentioned already, and equivalent quantity is added to the compressor, unlike the refrigerator. Now, the process fluid returns back to the original state by warm-up again through the heat exchanger. And the heat exchanger will have the high-pressure fluid entering from the compressor side to the Joule-Thomson side. So, therefore, the process fluid, returning fluid will warm up from low temperature to high temperature and go back to the compressor. Right. Now, what is the minimum work requirement to liquefy a gas? Okay, we have already discussed about this. We said that the best process that one can adopt for liquefaction of a fluid will be the one with the maximum efficiency, which is the Carnot cycle. What is the Carnot cycle consisting? The Carnot cycle consists of isothermal compression and adiabatic expansion. Okay, isothermal compression, isothermal adiabatic expansion, again isothermal expansion and adiabatic compression. These are the four processes which we normally use in the case of a Carnot cycle. Right. Now, of these four processes, we will right now utilize only two processes for doing the liquefaction. So, in this case, liquefaction essentially is an open-ended cycle because you are going to withdraw the liquid, and we will use the most efficient Carnot cycle for this purpose. We use only the two processes, process 1 to 2. Please see the diagram here in the TS diagram. The process 1 to 2 represents the isothermal compression. So the pressure is increased from position 1 to the position 2. And then the gas is now, adiabatically expanded, and the gas goes from position 2 to position 3, where it touches the saturation zone and becomes 100% liquid. Okay, so now this is the sort of process which we can think of. Okay, so now we can imagine a compressor. You can see the diagram below. So you take a gas in a compressor, the certain mass flow rate is entering the compressor, and then the compressor is adiabatically compressed, isothermally compressed, so the temperature rises, but the heat is rejected constantly. UR dot is the heat rejection, and then the gas at the end of the compression process increases to a pressure level, high pressure, and then it is expanded adiabatically through the expander, and the expansion process is perfect, and therefore 100% of the fluid is totally liquefied, and you collect the liquid, and which is collected here in the reservoir. Okay. This is what we have as the process what we talk about. Now, we assume 100% efficiency for the compressor, 100% efficiency for the expander for our assumptions to calculate the minimum work requirement. Okay, now to calculate this, we use the first law of thermodynamics, which says that if a certain quantity of heat is given to a system, then it goes for two purposes, namely to change its internal energy or enthalpy of the system, plus certain amount of work is done. So we can rewrite this in a different form because we are going to consider this for a flowing system. So we write now Q dot net is equal to W dot net plus summation of the enthalpy of the outlet zone, outlet flows minus summation of enthalpy of the inlet flows. Okay. So bringing that W dot net back to the left side, so you can write Q dot net minus W dot net is equal to summation of the outlets of enthalpies minus summation of inlets of the enthalpies. Okay. When we talk about enthalpy, we are referring to the enthalpy of the fluid, okay, which is in the process. Now, we apply this to the present case. If you apply to the present case, what about the enthalpy change? The initial enthalpy is H1, and then the enthalpy becomes H2 when the pressure rises to H2. Pressure is now at the position 2. And but since H2 is also same as HF because it's vertically down, so it is also same as HF, and therefore we can write this as QR dot, which is the heat rejected, minus the work output minus W dot net is equal to M dot, which is the mass flow rate, okay, into enthalpy of the outlets is HF minus enthalpy of the inlet is H1. Now, please note, we are using here the specific enthalpy values. That's why the mass flow rate is getting multiplied. Obviously, HF is smaller than H1. So we can rewrite this expression as minus M dot into H1 minus HF. Okay, that's the equation number 2. What about the heat rejection? What sort of heat rejection is taking place? QR dot is the heat transferred during the isothermal compression. So we can write it as QR dot is equal to M dot T1 into S2 minus S1. Okay, in a TS diagram, you can write the Q is equal to T. We use just the formula Q is equal to TdS, right? Temperature into change in the entropy. So if you apply for this isothermal process, temperature remaining constant, the entropy changes from the initial value S1 to final value S2. So QR dot is equal to M dot into T1 into S2 minus S1. Here again, S2 is nothing but SF. Okay, please remember that. And therefore, we can write like M dot T1 into SF minus S1. But since we know very well S1 is greater than SF, we write it as minus M dot T1 into S1 minus SF. Okay, so we now have an expression for the QR dot minus W dot net. We have got an expression and also an expression for QR dot we have been able to get. Now we substitute the expression for QR dot in the previous equation number 2. When we do this, then we get W dot net minus W dot net is equal to M dot T1 S1 minus SF minus M dot H1 minus HF. Okay, so this is what we are getting. You find that if you divide throughout by M dot, you will get minus W dot net by M dot is equal to T1 into S1 minus SF minus H1 minus HF. Now, the right-hand side is a positive quantity. Okay, the entropy change term is much larger than the enthalpy change term, and therefore the right-hand side is positive. What it shows is minus W dot net by M dot is therefore positive, and which means W dot net is negative. So liquefaction process is essentially a work absorbing process. That means you have to add work to liquefy a gas. Okay. In an ideal case, all the gas entering the compressor is liquefied, okay, and therefore we can write M dot F by M dot is equal to 1 in the present case. Okay, so in our case, the complete liquefaction is taking place, so we can write the yield. This the term M dot F by M dot is the yield, and this value is equal to 1. Okay, that's what we are going to assume, right? Okay, now let us find out what is the ideal work for liquefying, let's say, different gases. We can have different gases like air, nitrogen, oxygen, hydrogen, helium, etc. We can start with 1 atmosphere pressure at 298.15 Kelvin. That can be our initial temperature. And then we can calculate what is the energies of liquefaction for in units of joules per mole or kilowatt hour per kg or kilowatt hour per pound. Like that we can calculate. So you find for air, this value is 20,900 joule per mole and the kilowatt hour per kg will be 0.2. For nitrogen, it is 21,400 and 0.21 kilowatt hour per kg. For oxygen, it is 20,300 joules per mole is the energy of liquefaction. And in terms of kilowatt hour per kg is 0.18. For hydrogen, it is 23,800 and kilowatt hour per kg is 3.30. For helium, it is 27,200, so many joules per mole, whereas for kilowatt hour is actually 1.89. The above table gives the minimum work requirement and any practical liquefaction system should try to approach these values. Now you notice one important thing, that the pressure at the end of the isothermal process is pretty high, as much as 10 to the power 7 psi, pounds per square inch, which is normally very difficult to obtain in the laboratory systems. So practical systems, actual systems will not be using this high pressure because it's very, very difficult to design your compressor, all the heat exchangers, etc., to withstand such high pressures. So what about the use of these numbers? These numbers can now be used for comparing to that of the practical systems, right? So that's what the utilization of. Let us talk about the induced evaporation. This already we discussed also in the last lecture. However, we'll redo it again. Historically, this is one of the earliest methods for obtaining low temperature. Now, what you do is you have the working fluid is compressed and cooled. By the process of cooling, it gets liquefied. That means the compressor and cooling, the gas gets liquefied. Now the compressed fluid is to pass through a throttling valve or it expands. And once it expands and into a low pressure coil, it flashes into a vapor and thereby the temperature is decreasing further. Okay. This cooled vapor cools surroundings or maybe a subsequent fluid, as in the case of a cascade process. So the early recorded ice making machine is based on this principle of what is called induced evaporation. Okay. Now, this almost the same principle is also used in the household refrigerator. So you can see in the figure, whatever that is shown here, you have a compressor, gas is compressed by the compressor, and then it passes through a coil where it is getting cooled. And at the end of the cooling process and high pressure, it becomes a liquid. Then when you throttle, the temperature drops further and it tries to cool the next part of the gas, another gas. Okay. So this particular process is the methodology which have been used in the early times for making ice. Okay. Now, in the case of a cascade process, one normally takes a set of gases. Okay. Now, the first gas should be such that it is cooled directly by compression alone. It is cooled and then become liquid by compression alone. Now, this gas is evaporated rather, rapidly evaporated, okay, such that it cools further down below its normal boiling point, and then subsequently it cools another gas which is close by in another part of the heat exchanger, and thereby bringing the second gas to its temperature below its TC. So by pressure alone, the second gas can now be liquefied and so on. So this process continues. This we already discussed last time. Okay. And for example, if you want to liquefy, let's say, nitrogen, you can start with ammonia and then use ethylene, methane in the process and finally come up to nitrogen. Or you can also have another cycle wherein Freon 22 along with Freon 13 and along with Freon 14 and then finally liquid hydrogen. Now, thermodynamically, this is supposed to be a very efficient process, but practically very cumbersome because you have to deal with the multiple subgases and many heat exchangers are involved, and leak tightness is very, very essential in all these cases. Okay. The process was also limited for use up to 60 Kelvin because people at the earlier time could not find gases below this temperature. Right. Okay, let us come to the adiabatic. Before we go to adiabatic, we'll talk about the isenthalpic expansion. In the isenthalpic expansion, it was found in 1853, J.P. Joule and W. Thomson observed that a gas under pressure gets cooled when forced through a constriction. This is known as the Joule-Thomson expansion. It is also known as the isenthalpic expansion because in the process, the enthalpy is kept constant. Enthalpy of the gas is kept constant. You know what is enthalpy? Enthalpy is H is equal to U plus PV. Okay, the gas under pressure is passed through a constriction or an orifice or a porous plug. The gas does not perform any external work in the process. It is only an internal work that is done by the gas. The enthalpy is supposed to remain constant in an ideal process, and hence it is called an isenthalpic expansion. Now, to obtain the cooling, the temperature of the gas should be below its maximum inversion temperature. Okay. So you can see a picture on your screen, and in the picture on the screen, you can see the left-hand side, with a gas which is under high pressure and a porous plug in between, and then the right-hand side having gas molecules which are well separated. So obviously you see the left-hand side is having high pressure, right-hand side at low pressure, strong forces between the molecules on the left-hand side, and it results in weak forces after the expansion between the molecules in the RHS, and high internal and kinetic energy on the left-hand side, whereas low internal kinetic energy on the right-hand side. The high temperature of the gas now gets become low temperature of the gas on the RHS. Okay. Now we can calculate what is the Joule-Thomson coefficient. Now, what is Joule-Thomson coefficient? The Joule-Thomson coefficient is nothing but it is designated by mu Jt. It is nothing but dou T by dou P at constant S. That is change in temperature to change in pressure at constant enthalpy. Dou T by dou P at constant S. Dou T represents the change in temperature. Dou P represents the change in pressure. How much the temperature changes for a change in pressure when the enthalpy remains constant. This is known as the Joule-Thomson coefficient. Now, to get the Joule-Thomson coefficient, there are methodologies to calculate this Joule-Thomson coefficient, but I write directly here the expression. The expression is nothing but 1 over Cp into 2 T dou V by dou T at constant P minus V. Okay, this is the expression which you have for the mu Jt. If someone is interested to arrive at this mu Jt, you can arrive at this from the following. Suppose there are three variables, let's say T, P, and H. Then you get an expression as dou T by dou P at constant H into dou P by dou H at constant T into dou H by dou T at constant P equal to -1. So that will be the starting point. From there, you can arrive at these expressions. Okay, I'm not going to work out these things here, but if someone is interested, it can be easily obtained. Okay. Now, the mu Jt is given by the expression given in the given equation 2. And for a perfect gas, we know ideal gas, perfect gas, or ideal gas, PV is equal to RT. Okay, so dou V by dou T at constant P is equal to, okay, R by P, or in other words, R by P nothing but V by T, because we are talking about 1 mole of gas. Okay, so it is V by T. So if you substitute this, mu Jt turns out to be 0. So obviously what you find is the Joule-Thomson coefficient for a gas, an ideal gas, is 0. Okay. So a perfect gas will neither show a heating or a cooling by Joule-Thomson expansion. The reason is very clear, because there are no interaction between the gas molecules, and therefore there is no change in the energies of the perfect gas. Okay, there is no energy change in the perfect gas, and therefore Joule-Thomson coefficient will not produce any cooling in the case of perfect gas. But in real gases, where there is interaction energy between the molecules, then mu Jt is given by this expression. Mu Jt is equal to 2A by RT into 1 minus B by V whole square minus B divided by Cp into 1 minus 2A by RTB into 1 minus B by V whole square. Okay, this term is the denominator. But we notice one thing, that B by V is very small compared to 1. And we can also make a note that in the denominator, we can neglect the second term, okay, in the denominator other than 1. So if you see this, then the expression simplifies to 2A by RT minus B divided by 1 by Cp into 1 by Cp. Or in other words, mu Jt is nothing but 1 by Cp into 2A by RT minus B. Now, what we can notice is the following. If suppose the term 2A by RT is greater than B, Cp is always positive. So if you multiply these two, then this turns out to be a positive coefficient. So 2A by RT is greater than B. If you take a case, then mu Jt is positive. And suppose 2A by RT is less than B, then you have a condition where this mu Jt is negative. So if the mu Jt is positive, it will produce a cooling effect. If mu Jt is negative, it will produce a heating effect. Suppose 2A by RB is equal to the temperature Ti. Okay, then in that case, mu Jt is equal to 0. In other words, neither there is a heating nor a cooling for the gas. Now, in the picture here, you can see the plot of temperature versus pressure is given, and the constant enthalpy curves are all plotted. And you can see that peak points of these curves are all falling in a line. Okay. And if any expansion takes place on the left side of this line, the dotted line, then it produces cooling. Whereas if anything happens, if you are having a change in pressure, the pressure is on the right x-axis and temperature on the y-axis. And the change in pressure causing on the any part of the curve on the right-hand side, then it produces heating of the gas. Okay. So this point corresponds to the Ta maximum value. Okay. So if the temperature of the gas is anything greater than this Ta maximum, it will always produce, okay, heating of the gas, right? So please remember this. So important condition for the Joule-Thomson expansion to produce cooling is that the gas temperature should be below its maximum inversion temperature. So now we can see here the table in which you have a set of details of various the gas as well as the Ta max values are given. So carbon dioxide 1500 Kelvin, air 602.7 Kelvin, oxygen 761.1 Kelvin, nitrogen 622.2 Kelvin, argon 722.2 Kelvin. Now there are three gases which are given on the right side of this table, which is neon 250 Kelvin, hydrogen 202 Kelvin, helium 40 Kelvin. You notice that for all these three gases, it is the maximum inversion temperature is below the room temperature. So which means for these gases, if you apply Joule-Thomson expansion, it will not produce cooling, rather it will produce heating. Okay, whereas the gases on the left side of the table, all of them will produce cooling on Joule-Thomson expansion. Okay, there is a physical understanding of the Joule-Thomson expansion. As you can see very clearly, mu Jt is nothing but, minus 1 over Cp into dou H by dou P at constant T. What is H? H is nothing but, we have already written that H is nothing but U plus PV. So you can take them as two terms, dou U by dou P at constant T and dou PV by dou P at constant T. The first term represents a departure from the Joule's law, which Joule's law says that the internal energy is a function of temperature only. But as now you see here, we are trying to find out what is the change in internal energy with respect to pressure. So it is a deviation from the Joule's law. Okay. The second term represents a deviation from the Boyle's law, because the product PV is nothing but at a constant temperature, it has to be a constant value. So the second term represents a deviation from the Boyle's law. So because PV has to be a function of temperature only for ideal gas. At low temperature, gases are more compressible and the attractive forces try to condense the gas. So second term is negative. Okay. And so mu Jt is always positive. At high pressures and elevated temperatures, molecules are close together and repulsive forces are brought into action. And this makes the second term more positive than the first term. So mu Jt becomes negative. So the heating of the gas occurs, and hence the Joule-Thomson expansion shows a heating in the process. Okay. So that is the physical understanding of this. Right. Let us move on to adiabatic expansion. The adiabatic expansion, gas is made to perform work using the work extracting device, and which is nothing but an expansion engine. So in the picture, you see a cylinder in which some gas is trapped. The initial position of the piston is shown by the dotted lines, and then the gas now expands and tries to move the piston outwards, and the whole system is completely isolated. Okay, and therefore there is no heat transfer from outside. So it's an isentropic process. Okay, so the gas is now expanding the piston and doing some work by the process. The work for doing this is coming from the gas itself, and the gas now drops in its temperature. Okay. Now again, as before, we can define the coefficient of adiabatic expansion as mu S, which is nothing but change in temperature to the change in pressure at constant entropy, which is nothing but dou T by dou P at constant S. What we will do is we will now use dou T by dou P at constant S into dou P by dou S at constant T into dou S by dou T at constant P is equal to -1. This is a thermodynamic equation which can be written for any three thermodynamic variables. If you do that, then you can write what is your dou T by dou P at constant S is. You have to take the other terms to the right hand side. When you do this, it is nothing but minus dou S by dou P at constant T into dou T by dou S at constant P. Okay. Now, dou S by dou P at constant T can be replaced by dou V by dou T at constant P with a negative sign, and therefore mu S turns out to be mu S is equal to dou T by dou S at constant P into dou V by dou T at constant P. Okay, this is what you get. Now, dou T by dou S at constant P is nothing but T by Cp. Okay, because you are multiplying TdS will correspond to dq, and that automatically Cp term, it's going to be constant pressure, and therefore Cp term will come into picture, but T is additionally added, therefore you have to divide by T, so you get that. Okay, it is Cp by T. Okay, and this dou V by dou T at constant P can be replaced from the coefficient of volume expansion as like this. That is minus beta is equal to 1 over V into dou V by dou T on constant V. And therefore, you find that combining all these terms together, you get mu S is equal to T by Cp into beta V. T by Cp into beta V is what you express. Now, in this right-hand side, temperature is positive. Okay. Cp is positive. The coefficient of volume expansion is also positive. And therefore, you will find the right-hand side term is 100% positive. At all temperature levels, this term is positive. Clearly, that at all temperature levels, you have a positive coefficient of expansion, and therefore positive coefficient, that means the adiabatic expansion produces cooling at all temperature levels. Now, what about the perfect gas? Even in a perfect gas, PV is equal to RT. So, dou V by dou T at constant P is equal to R by P, or in other words, it's equal to V by T. So, you can write mu S is equal to T by Cp into V by T, or T and T cancel, so it's nothing but V by Cp. So, even in the case of ideal gas, there is a finite coefficient of adiabatic expansion present. So, for real gases, we can write similar expressions. Dou V by dou T at constant P is nothing but R by V minus V divided by R by V minus V whole square minus 2A by V cube. So, and mu S can now be written as mu S is equal to V by Cp into 1 minus B by V divided by 1 minus 2A by VRT into 1 minus B by V whole square. So, you can simplify, assuming that volume is much, much greater than the small value of B. So, mu S is nothing but V by Cp into 1 minus V by V divided by 1 minus 2A by VRT. So, that is the expression what you have for the case of adiabatic expansion. Now, if you compare the adiabatic expansion and Joule-Thomson expansion, the adiabatic expansion produces cooling at all temperature levels, and adiabatic expansion is essentially an external work method where some amount of work is being done, okay, by the gas on the piston, okay, on the piston, and therefore there is a work extraction takes place, and the energy is coming from its internal energy of the system, and therefore the temperature of the gas drops down. Okay. Now, it need not be necessarily a piston cylinder arrangement. One can also use a rotary expander for in place of simple rotary expander system can also be used in place of a regular reciprocating type piston cylinder arrangement. Okay. Now we are going to talk about liquefaction systems for gases other than hydrogen and helium. Okay, historically, this liquefaction system is known as simple Linde-Hampson system. Now, what is simple Linde-Hampson system? We are going to briefly explain this now. It is one of the earliest, probably the second method which was used for liquefaction of gases, the first one being the cascade methodology. In this method, the working fluid has to be compressed to a high pressure. Then it gets cooled in a heat exchanger by the return stream and then expanded through a Joule-Thomson valve. Okay. Now we are going to consider the situation under steady state condition. So you can see on your right hand side of the screen a diagram which indicates a compressor. Gas is coming in, gas is getting compressed isothermally from an initial pressure to a final pressure, and then it passes through a heat exchanger. One part of the heat exchanger reaches the point 3 where it is Joule-Thomson, where it is expanded through in a Joule-Thomson valve, then becomes liquid. Some part of it becomes liquid and some part is taken out. and the part which is becoming a liquid is not available for return gas, and therefore the return gas which is passing through this now enters through the other part of the heat exchanger, and now the gas coming out is m dot minus mf dot. Okay, and this gas completely warms up and joins back to this. Since we are already taking out some part of the fluid is liquefied, so we need to add this additionally in the at the input, which is mf dot. Okay. Now you can see this diagram, the TS diagram. So first part is an isothermal compression between 1 to 2. Then 2 to 3 is corresponding to a constant pressure process of cool down. Okay, the pressure is constant, but the temperature drops to low value. And then at the point 3, it is expanded in the Joule-Thomson expansion takes place, goes to 4. So some part of it is liquefied, another part is vaporized, another part is a vapor, and then it is gradually warmed up in the return part of the heat exchanger back to room temperature. Okay. So you can see 1 to 2 is the working gas isothermally compressed, 2 to 3 is cooling of the gas at constant pressure in the heat exchanger, 3 to 4 is the jetty expansion. Okay, and some part of it is liquefied. The liquefied part is mf dot, and the remaining part is the cold vapor. And then 4 to 1 is the warming of the gas at constant pressure. Again, we can assume 100% efficiency for the heat exchanger, and now we will apply the first law of thermodynamics here. If you apply the first law, Q dot minus W dot is equal to summation of all the enthalpies of the outlets minus summation of enthalpy of the inlets. Let's apply the first law to the heat exchanger, Joule-Thomson, and reservoir. That means except the compressor, all the other components. If we do that, then the left-hand side term is 0 because there is neither the heat transfer is there nor the work done part is there. So it is 0 is equal to enthalpy of the outlets, which means the m dot minus mf dot into h1 plus m dot hf, that's your fluid enthalpy, what is coming out, but being coming out as coming as a fluid which is taken out. And then you have also minus the enthalpy of the inlet minus m dot h2. So if you rewrite these terms, then you can show that y is equal to, which is called the yield, which is mf dot by m dot, which is h1 minus h2 divided by h1 minus hf. Unfortunately, that hf part is not visible. That doesn't matter. Okay. So this is what is called the yield for the liquefaction process, or how much of the incoming fluid is getting liquefied. Now, the only parameter that now can be varied is H2, namely the enthalpy at the point 2. Okay, how to increase the yield? You have to increase the yield, right? So to do that, the only point that H2 has to be, you can modify H2. The pressure at the point 2 should be chosen such that H2 is minimum. Okay, H2 is minimum. So H1 minus H2 will be large. Okay, so yield will be the maximum. Okay, that's what will happen. So how do we do this? Then we have to take dou H by dou P at T is equal to T1 should be equal to 0 at this particular point. Sorry, it should be equal to 0. Now we can rewrite this expression dou H by dou P at constant Ts minus dou P by dou H, dou T by dou P at constant H into dou H by dou T at constant P. And that is nothing but minus mu Jt into Cp. The first term is the coefficient of Joule-Thomson expansion, and the second term is nothing but that Cp. Now Cp cannot be 0, but mu Jt can be 0. The coefficient can be 0. So we must choose a pressure at the point 2 such that the coefficient is practically equal to 0. Okay. So the pressure should be such that at that particular point, the coefficient is 0. This is what you have to select, the pressure value. So the value of pressure, which is normally in this case is about 400 atmosphere for air, but in practical system, one uses around 200 atmosphere. So this is for the yield method. Now, what about the work requirement? Now, the work requirement in this case can be calculated by applying the same, first law of thermodynamics to the compressor side. If you apply to the compressor side, then we can write Q dot net minus W dot net equal to M into H2 minus H1. H2 is the enthalpy of the outlets, minus H1 is the enthalpy of the inlets. What about heat rejected? Q or dot, that value is nothing but M dot T1 into S2 minus S1, or in other words, it's equal to minus M dot T1 into S1 minus S2, because S1 is larger than S2, so we are writing it properly. So now combining these expressions now, you get the ultimate expression as minus W dot by M dot is equal to T1 into S1 minus S2 minus H1 minus H2. You please remember this expression is almost the same as what we had in the case of ideal work for liquefaction, except for the fact that earlier it was SF, here it is SF and HF, whereas here it is S2 and H2. Okay, these are the values which we are choosing. Now, this is for the work requirement for unit mass of gas that is compressed. But if you want to calculate the work requirement for unit mass of gas which is liquefied, then you can rewrite it slightly differently. So you can write minus W dot by M dot, MF dot is equal to minus W dot by M dot into M dot by MF. Or in other words, is equal to minus W dot by M dot into 1 by Y. So you can write this expression as minus W dot by M dot, MF dot is equal to H1 minus HF by H1 minus H2 into T1 into S1 minus S2 minus H1 minus H2. So obviously you see that the work requirement will be fairly large because of the fact H1 minus HF is much larger than the H1 minus H2. Okay, so you are essentially dividing by the yield, which is a very small percentage, and thereby you are able to see a larger work requirement per unit mass of the fluid liquefied. Now we are going to discuss about the pre-cooled Linde-Hampson system. Now in the previous cycle of the simple Linde-Hampson system, the yield is of the order of 6 to 8%. A plot of the yield as a function of temperature of the gas at the entrance of the heat exchanger at different pressures is shown in this diagram. We notice that the yield increases by lowering the temperature of the gas entering the heat exchanger. Yield also increases by operating at high pressures, higher outlet pressures of the compressor. So what it means is, if you use a pre-cooling system, then we will be in a position, if you use a pre-cooling system, we will be in a position to increase the yield, in which a separate refrigerant such as carbon dioxide, ammonia, or freon can also be used. So this modified system, which uses the pre-cooling, is called the pre-cooled Linde-Hampson system. Okay. So it is advantageous to use a pre-cooled Linde-Hampson system so that initially the gas is already cooled down to some extent so that you are able to increase the yield of such a system. Right. Okay, now let us discuss about the pre-cooled Linde-Hampson system. So you can see on the right-hand side of your diagram, flow here. A diagram is shown here. So the lower part of this is the actual fluid liquefaction part. Okay. The original heat exchanger of a simple Linde-Hampson system is now split into two parts. Now, and the first part of it is utilized for pre-cooling by a separate refrigerant from outside. So that is all that the difference. So you have a certain amount of pre-cooling taking place by using a separate refrigerant. Right? That's what we are doing. Okay. So that means the pre-cooling is done by using a separate refrigerant from outside. Now we can apply the same, applying the first law of heat exchanger to Joule-Thomson valve, liquid receiver, and the heat exchangers. The first heat exchanger, Joule-Thomson valve, liquid receiver, etc. If you do that, the left-hand side W dot minus Q dot, Q dot minus W dot, that term is 0. So it is equal to enthalpy of the outlets minus the sum of the enthalpy outlets minus sum of the enthalpies of inlet. So you can write M dot minus MF dot into H1. That's because it's one of the outlets here. It's returning gas. Then plus M1H2, that's a gas which is entering the first heat exchanger. Sorry. MR dot by HA, this is your refrigerant part, plus MF by HF, which is the quantity which is liquid which is taken out, and minus M dot H2, which is the gas entry into the system, minus M dot or HD, which is again the refrigerant entry into the system. Now we can divide throughout by M dot and use MF dot by M dot as yield and MR dot by M dot as R. Then you get an expression like this. Okay, if you simplify, you get the expression Y is equal to H1 minus H2 divided by H1 minus HF plus R times HA minus HD divided by H1 minus HF. Now, you can see that because of the pre-cooling, there is a certain amount of increase in the yield. Okay, that yield is actually this second term, which is R into HA minus HD divided by H1 minus HF. The maximum yield for the pre-cooled system can be Y max is equal to H6 minus H3 divided by H6 minus HF. Okay, this is the additional yield. Right. Okay, this is the maximum value of yield. Okay. Obviously, what we are doing is we are bringing down the temperature from a higher position to the position of the refrigerant, which is the 3 and 6. Right. So obviously, the yield maximum cannot go below this value. Now, what about the work requirement? The work requirement again now is increased. The reason being that you have an additional fluid, refrigerant fluid, which needs to be processed, which need to be some amount of work requirement is there for having this refrigerant fluid there. So therefore, minus W dot by M dot is equal to T1 into S1 minus S2 minus H1 minus H2 plus R times HB minus HA. So this is the refrigerant influx, additional work due to having the refrigerant added in the system. Okay. So this is the behavior of the modified Linde-Hampson system. Welcome back to this presentation on gas liquefaction methods. We have been discussing the different methods for gas liquefaction. We started with the ideal liquefaction process, the work requirement for that. And thereafter, we have been discussing about the various other processes, starting with the induced evaporation, isenthalpic expansion, and Joule-Thomson expansion, etc. And then considering the gas like, air, oxygen, nitrogen, etc., other than hydrogen and helium, we have proposed methods of simple Linde-Hampson system and pre-cool Linde-Hampson system that have been discussed in the last lecture. Now, We will now talk about Claude liquefaction system. The Claude liquefaction system is a medium pressure cycle which operates at a pressure about 40 atmosphere. In this system, the energy is removed from the gas by allowing it to perform work on a piston cylinder arrangement. Okay. So you can see the pictorial representation of the expander. So now you remember, suppose you don't have this expander, then the whole thing is equivalent to a simple Linde-Hampson system. And but for the fact that the heat exchanger is now split into three parts. Okay, HE1, HE2, and HE3. Okay, other than that, you have the helium gas compressor. Okay, HE1, HE2, HE3 combined together will form the total heat exchanger of the simple Linde-Hampson system. And then you have a Joule-Thomson valve where then you have a liquid reservoir and then liquid is collected here. And then the return gas is coming back to cool the incoming gas and then comes back to the compressor. So what we do in a Claude system is the original heat exchanger of the simple Linde-Hampson system is divided into three parts. At the end of the first heat exchanger, the incoming gas, approximately about 70% of this gas is passed through an expander, and the expanded gas now will automatically be cold gas now. This cold gas is returned back in the path of the return line. So it connects between 7 and 8 in the return path of the gas stream. Okay, so that means you are able to extract certain amount of work from the gas by using the expander. Normally a simple expander can be a piston cylinder arrangement, simple piston cylinder arrangement. You can also use a turbine in place of piston cylinder arrangement for cooling. It's also possible to do that. So the gas after compression is passed through the heat exchanger HE1. At point 3, about 70% of this gas is passed through the expander and it is made to work, and the work is extracted and the cooling of the gas is taking place. So the cold stream from the expander is now returned along with the return stream, gas stream at the end of the heat exchanger HE2, and this cools the incoming stream again. So the gas at the end of the HE3 is expanded by the Joule-Thomson expansion valve, and part of the gas gets liquefied, and the cold gas is now returned at the end of HE3. It is now warm, goes back and cools the incoming stream of fluid. So if you look at the TS diagram, you can see the 1 to 2 will correspond to the isothermal process of gas compression. 2 to 3 is a constant pressure process of cooling down in the heat exchanger 1. At 3, about 70% of the gas is now expanded. Ideally, it has to be a vertical line, that is 3 to E, but practically it will be 3 to 8. That will be the slight variation, slight angle. Instead of vertical line, it is a slightly angle with a slope. Okay. Now, the incoming gas is continuously cooled down from 3 downwards. From 3 onwards, downwards, it gets cooled to 4, and then finally it reaches 5 at the end of the third heat exchanger. And at 5, it is undergoing a Joule-Thomson expansion, and the Joule-Thomson expansion takes the gas to position 6, where a part of the gas is liquefied, and another part is the gas which is comes back as a cold gas in the return stream. Okay. So now it combines and gradually cools the incoming stream and returns to the position 1. Since a part of the fluid is now liquefied, you add this additional mass at room temperature as mf dot into the system, right? Okay, now as before, I'm sorry for the quality of the slide, and the slide is not so clear, but anyway, I can read it up for you. Let's apply the first law to all components except the compressor. Then you can write minus W dot E is equal to M dot minus MF dot H1. Okay, the enthalpy of the outlets plus m dot hf, which is again one of the outlet, minus m dot h2. Now you can apply the first law only to the expander. Then you can write W dot E is minus W dot E is equal to ME dot into HE minus H3. What is ME dot? ME dot is the actual mass flow rate that is entering the expander. Okay, at the expander, the enthalpy changes from H3 to HE. So therefore, minus W dot E is equal to ME dot into H3 minus 3. So now you can substitute for minus W dot E and also take X as ME dot by M dot. Then if you do that, then on certain simplification, you get the expression for Y. I'm not going through all this write-ups here. You can read it up. So this will show you Y, which is the yield, is nothing but H1 minus H2 divided by H1 minus HF plus X into H3 minus HE divided by H1 minus HF. What does it show? It shows the yield is now increased. The increased yield now will be because of the fact that you are able to lose a certain amount of internal energy because of the expansion of work. So there is some particular fraction of the energy of the gas is lowered by the doing this external work by the gas in the expansion engine, and therefore increase is now increased. Yield is increased because of this expansion process. So the second term actually represents the increase in the yield due to the expansion process. Okay. Now the second term represents the improvement on yield over the simple Linde-Hampson system. And similarly, you can also calculate what is the work requirement. The work requirement per unit mass of gas compressed is exactly same as that of the Linde-Hampson system, except for the fact if you use the expansion work that is produced for compressing another gas, maybe, then in that case, that expansion work has to be taken into account. So you can write W dot by M dot minus W dot by M dot is equal to T1 into S1 minus S2 minus H1 minus H2 and minus of X into H3 minus HE. We are assuming the work output from the expansion engine is being utilized for cooling any of the gas, for compressing a part of the gas which is present. Okay. So for a given PA, so a given P2 and the expansion ratio X, we can calculate the work requirement, and this can be plotted, and the plot is shown in the bottom diagram here. And you can see for different P2 values and certain X values, what is the work requirement. For example, for 20 atmosphere, 40 atmosphere, 100 atmosphere, and 200 atmosphere. Two things we notice. One is the work requirement decreases, okay, with increasing X value for a given P2. Take one P2, for example, let's say 200 atmosphere. The work requirement keeps on decreasing with increasing X value. Okay, that is number one. Secondly, the minimum work requirement decreases. It keeps decreasing to lower X values with increasing P2. Suppose I am able to increase the pressure, then the minimum work requirement keeps decreasing. And that means for a given operating pressure of the cycle, X value has to be optimized to have the minimum work input into the system. You have to optimize the X value so that you are able to get the minimum work requirement. So that's what has to be done. Okay, utilizing these facts, what we are seeing here, we can think of what is called a Kapitsa system. The Kapitsa system is a modified Claude system. And this modified Claude system, what is the modification done? In this case, we are eliminating the third heat exchanger. And this is developed by Kapitsa in 1939. We can also use a rotary expander in place of the reciprocating expander. So what we are seeing here, for example, if you are able to reduce the pressure and increase the X value, then in that case, you can operate at lower pressures and higher X values, and thereby the work requirement can be reduced in the earlier cycle called Claude cycle. So we are making use of this here in the Kapitsa system. So you can use an expander in this case. You can also think of using a rotary expander in place of the reciprocating type expander. So the operating pressure of the cycle can be relatively low now. So of the order about 7 atmosphere. Since the rotary expander is used, some amount of liquefaction at the outlet of the expander is also permissible due to the rotary expander. Okay. So the first heat exchanger is essentially working as a regenerator. It combines the process of liquefaction, process of purification as well. Heat exchange as well as purification, it takes care, right? So we have the Kapitsa system, right? Now we can think of an alternate one. Suppose we operate for a pressure of 200 atmosphere. The expansion flow ratio, expansion engine flow rate is approximately about 0.6. And the optimum temperature before the expander is approximately room temperature. So therefore, one can omit the first heat exchanger of the Claude system by compressing the gas to about 200 atmosphere. So what we can do is, instead of deleting the third heat exchanger, now we can delete the first heat exchanger and compress the gas to about 200 atmosphere. So the Haaland system is nothing but the Claude system with the first heat exchanger omitted, and the compressor is operated at a high pressure. So if you operate around 200 atmosphere, then the you can now omit one of the heat exchangers, and thereby we'll be able to have a high pressure system. That's what you will be able to by omitting the first heat exchanger. The advantage with the Haaland system is lubrication problems are overcome because you are essentially operating all this at near room temperature. So the air enters room temperature, at room temperature into the expander, and leaves approximately at about 270 Rankine. And so light lubricants are only needed. Now, in the Haaland system, expansion engine, Joule Thomson approximately contribute equally, whereas in other system, expander makes by far the largest contribution, right? Okay. Now, let's try to compare the different liquefaction systems. Now, in this chart, whatever that is given here, you have the list of liquefaction system and the yield for such system, and then the work requirement, okay? And there is a last column which says figure of merit. The work requirement is the work required per unit mass of the fluid liquefied, right? That's what is given here, minus W dot by MF dot. It is in units of BTU per pound, but doesn't matter for us. Anyway, we are only going to compare. Okay, let us consider the ideal system. In the ideal system, yield has to be 1. And we are talking about liquefaction of air. So therefore, 1 atmosphere at about, let's say, 21 degrees centigrade. And the work requirement is about 308 British thermal units per pound. So the figure of merit in this case is 1. Now let us consider Linde-Hampson system operated at 200 atmosphere, and let's assume the efficiency is 100% for the compressor, and we will take the Linde-Hampson system efficiencies as 1 for the heat exchanger. So in such cases, you find the work requirement is about 2250 BTU per pound mass, whereas yield is only 8.6% approximately. So the figure of merit will now be 308 divided by 2250, which is about 13.7% or 0.137. The observed Linde-Hampson system is much lower. It is 4440 BTU per pound mass, and the figure of merit is only something like 7%. Coming to pre-cooled Linde-Hampson system, the pre-cooling occurring at about minus 45 degrees centigrade, then you have an increased yield of about 0.179 theoretically, and the work requirement per unit mass of the fluid is 963 BTU, and the figure of merit will be only about 0.32 or 32%. Observed Linde-Hampson system again, yield data is not available. This is about 2,400 BTU per pound mass. So it's about 11.9% only. Claude system, for example, if you consider a 40 bar as the pressure and X value is about 0.7, that is the ratio of the gas which is going to the expander, which is about 0.7. The efficiencies of the expander and compressor all are taken as 1. So in such cases, yield is about 26%, whereas the work requirement is 382, so many BTU per pound. Figure of merit is approximately 80%, 80.8%. Okay. Claude observed is actually 1,540 BTU per pound, and only about 20% is the figure of merit. The Haaland system, for example, P2 and P3 is about 200 atmosphere, and the efficiencies are taken as 1. The yield is about 37%, and the work requirement is 367 BTU per pound mass, or in other words, the figure of merit is about 82.1%. Observed Haaland system is about 1430, okay, and so many BTU per pound mass, and the last one is 0.216 is the figure of merit. Okay, I will stop with this one. Next, we'll move on to the next one. Now what we are going to do is, we are going to consider the liquefaction system for neon, hydrogen, and helium. Okay. What is so special about neon, hydrogen, and helium? We know very well, for these gases, Joule-Thomson expansion will produce heating. So, liquefaction system without pre-cooling is not suitable for these gases because the Ti max is less than the ambient temperature. So, we have to discuss the liquefaction system for hydrogen and helium. Hydrogen and neon, let's say. We'll start with helium, we'll do it separately. Hydrogen, neon, we'll consider. All that we need is, we have to pre-cool the gas. So, we have to apply what is called the pre-cooled Linde-Hampson system. By pre-cooling the gas, the temperature of the gas is lowered such that the temperature of gas entry to JT is below its TA maximum value. So what are the pre-cooling fluids one can choose? One can choose fluorine, argon, oxygen, air, methane, and nitrogen. These things can be used. Of all these, liquid nitrogen is quite suitable because of its inertness and easy availability. Right. So let us consider the Claude system for hydrogen and neon. The Claude system contains an expansion engine, and hence it can be used for all these gases because you don't need to do a pre-cooling in the Claude system, but you can also do a pre-cooling if you want. If you do that, the liquid nitrogen pre-cooling enhances the figure of merit. Figure of merit goes up by 50 to 75% when compared to the pre-cooled Linde-Hampson system, and thereby you will be able to have a higher production by the pre-cooled system, pre-cooled Claude system. Right. Now, hydrogen liquefaction is done in a different way. One can think of a helium refrigerated hydrogen liquefaction system. Helium is actually pre-cooled to liquid nitrogen temperature and thereby expanded in an expander which produces the cooling required for hydrogen. The helium refrigerator is a modified Claude system in which helium is not liquefied but still kept cold and its temperature should be cooler, temperature should be lower than that of the liquid hydrogen temperature. Okay, but it will remain as a gas. So the hydrogen gas can now be pre-cooled with the liquid hydrogen, and then the hydrogen gas can be initially pre-cooled with liquid hydrogen, and thereafter it gets liquefied because of its heat transfer, heat exchange between the refrigerated helium gas. So the advantage of this type of system is it is a low pressure cycle and has also the compressor pressures are less, and so the compressor pressure size, the size of the compressor is considerably small. Okay. And so this is one of the methodologies which have been adopted. In fact, all over the world, people use this because it's a much easier method of producing liquid helium. I believe even the system which is being adopted in Mahendragiri of ISRO, this same procedure is being used. Okay. I have to discuss an important topic relating to hydrogen. This topic is known as the ortho-para conversion of hydrogen. What is ortho-para conversion? Now, hydrogen exists as a molecule. It does not exist as an atom, but rather it exists as a molecule. On the other hand, if you look at helium, helium exists as an atom. Helium need not be a molecule. Okay, helium can remain as an atom. Hydrogen exists as a molecule. That means two hydrogen combine together to form H2. Okay. So when they form H2, what about the spins, nuclear spins? The nuclear spins can be added together. Each hydrogen has a spin of half. So therefore, the spins can be half plus half. So they can be in one direction vertically. Please see my hand. Then it can be horizontal. It can be in the opposite direction. So therefore, the spins can be plus half, plus 1, 0, minus 1. This is what is called the ortho position, the ortho state. It can also have a spin in the opposite direction like this, plus half, minus half, the next spin is 0. So therefore, this position is known as the para state. So it can exist as ortho state or in para state. Okay. So this is the two states in which this hydrogen molecule can exist. Now, at room temperature condition, the ortho is approximately about 75% and 25% of it is in para state. Okay. And what happens is as you lower the temperature, there is a conversion of ortho to para, and at the boiling point of 20.4 Kelvin, 0.21% of it is only ortho and 99.79% of it is in the para state. So that's what happens. So there is a conversion of the hydrogen from the ortho state to para state. Okay. Now this happens during the normal liquefaction process. The gas does not immediately get converted. It tends to remain in the ortho state. But after the liquefaction is over, then the conversion tries to occur. But when it converts, a part of the liquid gets evaporated because the ortho-para conversion is an exothermic reaction. Okay, it is an exothermic reaction, and therefore the ortho-para conversion boils off certain quantity of fluid what you have already produced, okay, and converts it to vapor. So if you want to have the maximum quantity of fluid liquefied, then you have to take care of the ortho-para conversion during the liquefaction itself, right? So how this is done? What people do is they use certain catalysts during the process of liquefaction so that during the ortho-para conversion, the gas gets automatically converted to the para state. From the ortho state, it gets converted to para state. Okay. See, there are two methodologies which have been followed in this arrangement. For example, you can see in this figure here, There are two arrangements which are shown here. First, the gas nitrogen is pre-cooled, okay, and you use certain catalysts for this orthopara conversion. The catalysts that are generally used as hydrous ferric oxide, chromic oxide on alumina, charcoal, and silica gel, and nickel-based catalyst, etc. These are the catalysts which are generally used. So you have a cartridge which is cooled in liquid nitrogen. Gaseous hydrogen enters through that and get pre-cooled to liquid nitrogen temperature. And the catalysts ensure there is a certain amount of conversion of ortho to para. Okay, then it passes through a heat exchanger, one of the parts. Then a Joule-Thomson expansion is done. So the liquid now the gas gets liquefied, and then you collect the liquid of it in this one. Now, one of the methods is to have a catalyst embedded here, and whatever outgoing liquid is now passed through the catalyst so that the ortho-para conversion takes place in this particular part also, right? So now, because of the ortho-para conversion, there is certain amount of vaporization. That cold vapor will pass through this part and then comes as hydrogen vapor. This hydrogen vapor being a gas hydrogen, it will be combined along with the gaseous hydrogen at the inlet, right? The second method, what we normally done is the gas which is coming here is expanded to Joule-Thomson expansion and made into two parts. In the one path, it is expanding to produce the fluid here. In the another path, it is producing the fluid, but at the same time, the outlet of it goes through the catalyst and you collect the para-hydrogen. The second path, the second methodology is supposed to give a higher yield, almost twice the yield compared to the first methodology. Okay. So the ortho-para conversion is an important aspect of the hydrogen liquefaction. So unless this is properly taken care, you lose large quantity of hydrogen what is produced as vapor. Right. Now let us discuss the helium liquefaction system. Now we know very well right now that you can simply use a expansion engine, and that too a reciprocating expansion engine for producing helium. And this is one of the standard methodologies for making a helium liquefaction system. Now, the Samuel Collins of MIT, he made the development of a helium liquefier. It was, in fact, a commercial unit was built by him. And this represents one of the milestones in the cryogenic engineering. Okay. So what does this consist of? This consists of the standard arrangement of the Linde-Hampson cycle along with the two expansion engines and one Joule-Thomson valve. Okay. So you can now imagine that your heat exchanger of a simple Linde-Hampson system is now split into 5 components. So HE1, HE2, HE3, HE4, and HE5. Between HE1 and HE3, you introduce the expansion engine 1. Between HE3 and HE5, you introduce the expansion engine 2. As in the case of Claude system, the expanded gas which is cold, it is returned to the opposite stream along with the opposite stream so that the return stream can be cooled. The incoming stream can be cooled by the process. Now the TS diagram is shown here. 1 to 2 isothermal compression, and then 2 to 3, and then at 3 you have an expansion. Cold gas is produced, and that goes back to, along with the return stream, back to the room temperature. It cools part of the income. Then you have from 3 to 4 and 4 to 5. Okay, at 5 again you have one more expansion taking place. That's adiabatic expansion taking place. And then the gas gets cooled. The cold gas again is returning back to to cool the incoming fluid. And at let us say the point 6 and 7, The gas is now expanded by Joule-Thomson expansion. Part of the gas becomes a liquid as fluid. F is the liquid, and the part of the gas which is returning back along with the stream, such that the incoming fluid can now be equal to it. Okay. You will not go into the mathematics of the derivations of the yield, etc. We'll just put down the expressions only. So we can first see that there are two expansion engines in the system, and after expansion, the cold gas is sent to the return stream as is shown in the figure. Now the yield is equal to mf dot by m dot, and is given by h1 minus h2 divided by h1 minus hf, plus a part which is due to the first expansion engine, the change in the enthalpy divided by h1 minus hf multiplied by x1 representing the fraction of mass flow rate which goes to this expansion engine, plus x2, say x plus x2 into delta H E2 divided by H1 minus H2. Delta H E2 is the, again, the change in the enthalpy of the second expansion engine, enthalpy at the second expansion engine. Okay, x2 again representing the fraction of mass that goes to the second expansion engine. Okay, typically, if you consider x1 as 0.5, 0.25, x2 is 0.5, that is 50%, 25% is x1 and 50% is x2, and let's say the remaining 25% goes through the JT. Let's say the inlet temperature of the first expansion is 60 Kelvin and the outlet is 29 Kelvin. The inlet temperature of the second expansion engine is 15 Kelvin and the outlet is 7.8 Kelvin. If you use that numbers, then the yield of such a system is approximately about 12% or 0.12. Okay. The performance again can be further improved by using liquid nitrogen pre-cooling, and the yield can almost become twice by this process of liquefaction, by the process of doing this pre-cooling with the liquid nitrogen. Okay. Next, I am going to discuss another important liquefaction system developed by Simon. Okay, this is useful for making small quantities of helium to liquid state. I have a batch liquefaction of helium. This is known as Simon liquefaction system. What is the Simon liquefaction system? It consists of a metallic container, okay, a thick-walled metallic container, okay, through which helium can be filled inside. Helium can be filled into this container. It is surrounded by a zone where you can fill in hydrogen, okay. Both liquid hydrogen as well as hydrogen gas can be filled in here. And both of them, the whole thing can be covered by another chamber, okay, a chamber which can be filled with any gas or evacuated. So it is connected to the vacuum system. And this is pre-cooled, entirely pre-cooled, for example, using a liquid nitrogen temperature, pre-cooled to liquid nitrogen temperature. Okay, this is what is the system. Okay, what is normally done is first you start with the helium inlet at a pressure of about 150 atmosphere at room temperature. Okay, it is filled into this innermost container. Sorry, helium is filled into this innermost container. Now, the vacuum, the zone where you have the immediate vacuum vessel, the vacuum vessel which is surrounding the inner vessel as well as the hydrogen zone, is filled with helium gas. Okay. So there is a good heat transfer that takes place between the nitrogen and the innermost container which is holding the helium. Okay, now the gradually helium gets cooled, and then the temperature, you know, the gas pressure, first of all, is filled to 150 bar, that is 1 to 2, it is already run. Now 2 to 3, the pressure remains the same. More and more of the gas is being drawn inside to the helium is drawn inside this because, and also temperature dropping, it reaches the state 3. Okay. Now what is done is, now you evacuate this particular helium gas which is present in the vacuums by the vacuum system, and now you fill in hydrogen, liquid hydrogen, into this zone, which will now stay over this helium container and tries to cool the liquid helium, cool the helium gas. So the helium gas will be cooled from 77 Kelvin to 4 Kelvin, okay, to 20 Kelvin, which is the temperature of the hydrogen. Okay. Now the choice of liquid hydrogen is taken such that, okay, by the time it reaches 20 Kelvin, okay, you almost empty the hydrogen part. The hydrogen becomes almost empty. Liquid hydrogen becomes almost empty. So it is to be done by practical methodologies. So by a trial and error methodology. Okay. So now the temperature of the helium, which is present inside this inner vessel, is 20 Kelvin, and it is the liquid hydrogen temperature, and it is at a pressure of approximately 150 to 200 bar. Okay. Now what is done is the inlet line is closed and suddenly the outlet line is opened for the helium section. So what will happen is helium now will be isentropically expanded. So it drops from 5 to 6, okay, thereby producing liquid helium in small batches in this container. So helium will be collected in small batches in this container, right? So helium is now collected here, and this helium is useful for experiments in small. So the quantity of hydrogen, as I mentioned, should be chosen such that the solid which is formed on pumping down is sufficient to cool down the helium gas, and also the solid hydrogen sublimes before the adiabatic expansion. Okay. So the process of making batch quantities of liquid helium is by the Simon liquefaction system. Very useful to conduct small experiments using this. Okay. I am now going to talk to you about another refrigeration system. This is known as the Phillips refrigeration system. Robert Stirling, a Scottish minister, invented this cycle for use, and when invented originally, it was supposed to work as a heat engine. So he made use of it for developing a heat engine. In 1834, John Herschel suggested that this can be used also as a refrigeration cycle. Okay. Now, many liquid nitrogen plants all over the world, and sometimes some also of liquid helium plants, they are developed by Phillips Eindhoven, and they are based on the Phillips refrigeration cycle. Okay, what is the Phillips refrigeration cycle? It is like this. It consists of the following components. It has a compression space. Let's say it has a totally working space, a space for the working fluid, this complete working space. The working space can now be divided into a compression space and expansion space. The compression space is here. This zone is the compression space. Expansion space is the opposite one. Here, compression expansion space. Okay. Now, in the compression space, when the gas is compressed, gas will become hot. The heat of compression can be removed by using water cooling arrangements. So you can see there is a water cooler here present. Okay. Now, the gas now passes through a regenerator, which is supposed to be one of the very important component of the system, which is a regenerator, okay, or a very specialized heat exchanger. Okay, afterwards, the gas now goes to this opposite side where it is cools with by a heat exchanger. Okay, it cools down by a heat exchanger and goes to the expansion space. Now the gas where it gets expanded is an isothermal expansion again, and thereby by the isothermal expansion process, the gas produces the cooling, okay, or in other words, the gas, whatever that is flowing around this, gets cooled to the lower temperature, or the refrigeration is produced, okay, by this process. Okay. So now you have two isothermal process and two constant volume process, which makes the total system as a refrigeration system. This is known as the Phillips refrigeration system. So two isothermals and two constant volume process, which is represented here in the TS diagram. So you can see the saturation curve occurring at a very low temperature here, and considering the pressures and temperatures, pressures and volumes here, you can see 1 to 2 is an isothermal compression, 2 to 3 constant volume process of reduction in volume, 3 to 4 is isothermal expansion, and 4 to 1 back is constant volume process. Okay. So this is the process. What is the assembly? The assembly consists of a piston, a displacer. So within the piston, one within the other, and the mechanism has a common crankshaft with different connecting rods and a phase difference. Now the job of the compressor piston is to compress and expand the gas, whereas the displacer job is to essentially move the gas from one location to another. Okay. Now the working space is divided, as I already mentioned, it is divided into compression space, expansion space, and along with the regenerator in between, which is a critical component, which is nothing but a highly efficient heat exchanger. Okay, let us look at the cycle of operations, and they are as follows. First, the displacer is at the topmost position. So please remember this. This is the displacer part. Okay, piston, compressor, and expansion piston is here. So with the displacer at the topmost point, the piston compresses the gas, and the heat of compression is removed by circulating cold water through the water cooler. Okay. So this is supposed to be an isothermal compression process. Practically, it may not be so, but theoretically, it is an isothermal process. Okay, with the piston in the uppermost position, the piston has moved up to this point. Now, the displacer is allowed to come down. It moves from the topmost position, it comes down. And there is no gap between that and the regenerator. So all the gas that is present here has to pass through the regenerator to the opposite side. So during the process, the gas gets cooled at constant volume and acquires the cold available in the regenerator from the previous cycle. Okay, the gas is now cooled, but it's a constant volume process. Now in the next process, 3 to 4, both the piston and the displacer move downwards. What happens is, in such a case, the gas is undergoing an expansion in the expansion space. This again is supposed to be an isothermal expansion. By this process, the cold is produced and the heat is absorbed from the surroundings, so that it is an isothermal expansion process. With the piston at the lowest position, the displacer is now moved upwards. This is now, we are talking about the last process, 4 to 1. So it is moving upwards, so that the gas is now forced through the regenerator and it's now returning back to the working space. So what we have is, we have again the same conditions at the very beginning, that is displacer at the topmost position and the piston at the below, so that it is ready for compression. Right? Okay. So what we notice is there are 4 processes that we have seen. One is isothermal. 1 to 2 is the isothermal compression. 2 to 3 is constant volume process, where the gas gets cooled. And 3 to 4 is isothermal expansion. Okay. And 4 to 1 is constant volume process, where the gas gets heated. So essentially, we have two isothermal process and two constant volume process. Now heat is rejected by the gas, and that heat rejection takes place okay, at the first process. When the isothermal compression process, heat is getting rejected. So you can write it as heat rejection is QR is equal to, or QR dot, if you would like to put it as QR dot, is equal to M into T1 into S1 minus S2. Now heat absorbed by the gas in the other process, that is the process from 3 to 4, is M into T3 into S4 minus S3. S4 is the final value and S3 is the initial value. Final value and initial value. So the net work done by the system now is QR minus QA. Okay, that is M into T1 minus M into T1 into S1 minus S2 minus T3 into S4 minus S3. Okay. So what is the efficiency, or we will call it a COP now. A COP is heat absorbed divided by the work input into the system. So heat absorbed is T3 into S4 minus S3 divided by T1 into S1 minus S2 minus T3 into S4 minus S3. So you can write this as can call it as COP is equal to T3 divided by T1 into S1 minus S2 divided by S4 minus S3 minus T3. Okay. Now let's assume that you are going to use ideal gas in the fluid, in the cycle. In this system, let's assume that you are using ideal gas. If you are using ideal gas, S1 minus S2 can be written in terms of the expression for ideal gas, that is CV into ln T1 by T2 plus R into ln into V1 by V2. Now, since T1 is equal to T2, it's an isothermal process. So we can write S1 minus S2 is equal to, so the first term actually cancels because T1 minus T2 will be T1 equal to T2, and therefore first term doesn't exist. It is logarithm of 1, which is 0. So we are left with S1 minus S2 is equal to R into ln V1 by V2. Similarly, for S4 minus S3, the temperature again is constant. So the first term cancels. First term is 0. So S4 minus S3 is equal to R into ln V4 by V2. Let us see some interesting things here. V1 is equal to V4 and V2 is equal to V3 because we are considering constant volume processes. Okay. Since they are constant volume processor, V1 by V4 should be equal to, V1 by V2 should be equal to V4 by V3. Okay. Because of this, then what happens is the S1 minus S2 should be same as S4 minus S3 because it is R into ln V1 by V2, which is nothing but R into ln into V4 by V3. So if you substitute this term, the ratio S1 minus S2 divided by S4 minus S3 is equal to 1. So the so-called COP or efficiency of the system, we will rather call it a COP of this Phillips refrigeration system, is equal to T3 divided by T1 minus T3, which is nothing but the Carnot cycle value. So what it clearly shows is, if you use a Phillips refrigeration cycle for liquefaction, then the COP of such a system is the same as that of the Carnot cycle. That's what you understand. So the efficiency of Phillips refrigeration system is equal to that of a Carnot cycle if we assume that a perfect gas is used in the cycle. Now, however, the figure of merit decreases in the actual cycle because of other reasons. One of the reasons is that there are mechanical losses in the drive unit, there are pressure losses in the regenerator, there is a finite temperature difference in the regenerator, etc. So you have losses due to all this. Okay. We talked about the refrigeration cycle. The practical cycle may not be as you see here, but rather little almost like a complex geometry. So you may have losses because of various other reasons. Philips Research Laboratories at Holland, they developed liquid nitrogen plants which are being used all over the world using this Philips refrigeration cycle. Okay. And they made plants which are having a single cylinder system or a four cylinder. I'm explaining that what it is. The single cylinder system is will have only one piston cylinder arrangement and it produces 6 liters per hour of production of liquid nitrogen. And PLN 430 is a four cylinder machine. That means there are four cylinders in which four piston cylinder arrangements are there. They are all connected to a common crankshaft and it is capable of producing 30 liters of production of liquid nitrogen per hour. Okay, that's the sort of production what it gives. Okay, the Philips refrigeration system units originally, now it was moved over to another company called Sterling Cryogenics. And now the Sterling Cryogenic people are now marketing these products all over the world. I must discuss one important aspect, which is called the regenerator effectiveness. The regenerator in a Philips liquid nitrogen plant is a very critical component. The reason being, first of all, it is sandwiched between the high temperature at one end and the low temperature at the other end. The ends are maintained at room temperature and the liquid nitrogen temperature, and it has a gradient and a very sharp gradient across its length. Now, what is the regenerator? The regenerator material will be normally made out of fine wool, okay, of I think it's a SWG standard wire gauge is approximately probably 36, 37 of that order. Okay, ideally, the temperature of the gas entering and leaving the regenerator should be the same as that of the regenerator at the respective positions. The regenerator, the earlier times have been made out of a copper wool matrix such that it transfers large, there's a large surface area and there's a high heat transfer coefficient. But what is noticed is that if the efficiency of the regenerator is 1% low, it affects the performance of the system and you lose approximately about 20% of refrigeration in the process. For 1% loss in efficiency, you lose 20% of refrigeration is lost. In other words, it means if the regenerator is inefficient by 5%, you do not produce the liquid nitrogen at all. Okay, because the efficiency drops to the refrigeration efficiency is dropped to 100%. So you don't produce refrigeration, you don't produce enough cold for producing the liquid cryogenic fluid. Okay, so that means the development of regenerator is a very important aspect. Development and use of a proper regenerator is an important aspects of Philips refrigeration system. And people are now trying out, instead of using the copper wool regenerator, they use stainless steel sintered matrix regenerator. And they are being tried out by 3D printing methods as well. Okay, there are a lot of research going on in this direction, and people interested should go through the present research scenario in this area. Coming to the liquid helium plant, Philips also has developed a liquid helium plant based on the same Stirling cycle arrangement. In the liquid helium plant, they use actually two expansion spaces. The displacer is designed such that there is an intermediate expansion space is available. Okay, so the two regenerators are used in this case. The first one between the room temperature and the intermediate temperature, and the second one is between the intermediate temperature and the final temperature. The first one is normally a phosphor bronze regenerator, while the second one is a lead regenerator. Liquefaction is achieved using the Joule-Thomson expansion ultimately. And there are very, very compact heat exchangers that have been built. And see, the total system has been developed by Philips. And the earlier unit model PLHE210, okay, that represents Philips liquid helium plant. It has okay, two expansion engines systems. Okay, there are two units of expansion engines on this system, and it has a production of about 10 liters per hour of production. Okay, that was system, but I don't think these plants are being fabricated anymore. Okay, because there are better plants available over the market. Okay, I thank you for your patient listening. I think we have more or less completed the topics of gas liquefaction methods. Okay, and we will move on to the next topic in another lecture.